You know that one friend, right? The one who can just glance at a confusing map and instantly know which way is north, or who reads an IKEA furniture manual like it's a simple comic book? Well, is that just some natural-born gift, or is it a skill literally anyone can develop? The answer is absolutely crucial, because there's a massive direct link between those spatial skills and your success in STEM, science, technology, engineering, and math. Welcome. In today's deep dive, we're unpacking a groundbreaking piece of research that totally flips the script on our cognitive abilities. We're going to explore just how malleable your mind really is when it comes to understanding the physical space around you, and why that is a total game changer for the future of education. Let's get into it.
Section 1. Study Identity. Let's look at the credentials and origins.
Whenever we dive into a major academic paper, establishing the credentials is our very first step. The research we're unpacking today is titled The Malleability of Spatial Skills, a meta-analysis of training studies. It was published back in 2013 by David H. Uttal and his team. Now, this wasn't just published anywhere, folks. It landed in the Psychological Bulletin. If you don't know, that is one of the most prestigious journals in the entire field of psychology, meaning it takes extremely rigorous data to get published there. The work was spearheaded by experts based in the U.S., specifically out of Northwestern and Temple universities. So we aren't just looking at some casual survey here. We're dealing with a heavily vetted foundational pillar of modern cognitive research. Section 2. Aim and question. What exactly are we trying to solve here? At the absolute core of this research is a question that taps straight into the classic nature versus nurture debate. To what extent can experience and training actually alter a person's spatial abilities? And, if they do change, are those effects enduring? Can they transfer over to other fields? The stakes here are incredibly high. For decades, there was this widespread belief that you're basically just born with spatial reasoning abilities, or you aren't. And if spatial skills are fixed at birth, well, then success in complex STEM fields might seem like an exclusive, closed club. But what if these skills are malleable? If they are, then the doors to science and engineering are blown wide open for everyone. So the researchers really wanted to know, can we actually train the brain to see the physical world differently? So their primary aim was to comprehensively meta-analyze the magnitude, moderators, durability, and generalizability of spatial skills training, ultimately to improve STEM education. But let's actually break down what durability and generalizability mean in this context. Durability asks a super practical question. If you train your brain today, are you still going to have that enhanced skill 6 months from now? Or does it just fade away like a forgotten password? Generalizability or transferability asks something even more exciting. If you practice, say, solving a 3D puzzle in a training environment, does that suddenly make you better at a real-world STEM problem, like visualizing a complex chemical molecule? The researchers didn't just want to win a theoretical argument here. They wanted actionable, real-world solutions for classrooms. Section 3. Methods and sample. How exactly was this done? To find answers to these massive questions, the researchers didn't just run a single isolated experiment. No, they gathered data from a staggering 206 distinct, independent studies. That is a massive sample size. We're talking about tens of thousands of participants spanning literally all age groups, education levels, and both men and women. Across all these studies, they extracted exactly 1,038 different effect sizes. You can think of an effect size as a mathematical measurement of just how big of a difference the training actually made. By combining 206 independent studies, they completely eliminated the risk of just relying on one small, quirky experiment. They essentially pooled a quarter-century of valid scientific literature into one giant, highly reliable dataset. The methodology they use to handle all of this data is called a quantitative meta-analysis. If you've ever followed a political election and seen a poll of polls, where they take dozens of different surveys and average them out to get the most accurate prediction possible, well, that's essentially what a meta-analysis does for scientific research. For data collection, they looked at various spatial tasks and tests, like mental rotation exercises. And to analyze it all, they used advanced statistical tools called Hedges-G and robust variance estimation. Don't worry, you absolutely don't need a math degree to understand this. All it really means is that they used the strictest possible mathematical filters to account for the differences between hundreds of different studies. It just ensured their final answer was rock solid. Now, rather than lumping all spatial skills into one big, messy category, think of these skills perfectly organized on a 2x2 grid. On one axis, we have intrinsic versus extrinsic skills. Intrinsic refers to the internal structure of a single object, while extrinsic is all about how different objects relate to each other or to the surrounding environment. On the other axis, we have static, meaning stationary, versus dynamic, meaning moving. Let's use an everyday example to make this concrete. Recognizing the specific shape of a rake lying on the ground, that's intrinsic and static. But imagining how that rake would look if you spun it around in the air, that's intrinsic and dynamic. Now, looking at a map to figure out where you are is extrinsic and static, whereas actually navigating your way through a bustling city on foot, well, that's extrinsic and dynamic. The researchers wanted to see exactly how training impacted each of these 4 distinct types of spatial reasoning.
Section 4, Key Findings and Conclusion. What did the data actually reveal?
Okay, so the crucial point is this. Spatial skills are definitely not a fixed fate. After crunching the numbers from hundreds of studies, the data revealed 5 golden findings. First up, they found a highly meaningful improvement with an effect size of 0.47. In the world of statistics, that's a really significant leap. It proves that training genuinely works. Second, this training is durable over time. It doesn't just disappear after a few days. Third, the skills transfer. Training in one specific spatial task actually makes you better at completely new, unpracticed spatial tasks. Fourth, and this is a massive one for debunking old biological myths, both men and women improve equally from this training. It proves once and for all that spatial reasoning is absolutely not bound by gender. And fifth, the individuals who initially scored the lowest on spatial tests, they actually benefited the most from the training. How cool is that?
The paper states, spatially enriched education could pay substantial dividends in increasing participation in mathematics, science, and engineering. This ultimate conclusion really changes everything. When the researchers say this could pay substantial dividends, they aren't just talking about students getting slightly higher grades on a high school geometry test. They're talking about a fundamental shift in our future workforce. By enriching education systems with intentional spatial training, we can directly increase the number of capable, confident people entering science and engineering fields. It turns out the foundational building blocks required to succeed in these complex, highly technical careers are entirely trainable. Section 5, Educational Impact and Bibliography. Let's wrap this up. This research serves as a very clear call to action for educators and policymakers everywhere. If we truly want to close the achievement gaps in STEM fields, we need to implement spatially enriched curricula. Instead of just memorizing mathematical formulas, students need active practice in 3-dimensional thinking and mental visualization. This shift moves us away from the outdated myth of innate talent and focuses strictly on what can actually be taught. The core pillars of this educational reform are perfectly captured by the study's key words: spatial skills, training, meta-analysis, transfer, and STEM. These aren't just academic terms. They are the literal foundation for a much more inclusive approach to science education. To formally credit the foundational work we've unpacked today, the full APA citation for David Uttal and his team's 2013 publication in the Psychological Bulletin, along with its digital object identifier, is up on the screen and serves as our anchor. It brings us back to one incredible truth. Whether you're playing a 3D video game, folding origami, or practicing engineering drafts, you have the power to reshape how your brain perceives the world. The limits of your mind are far more flexible than you might have ever thought. So, knowing what you know now from this deep dive, what are you going to do to train your own spatial skills today?